Welcome to today's paper reading. Today's paper is titled, From Artificial Needles to Real Haystacks, Improving Retrieval Capabilities in LLMs by Fine-Tuning on Synthetic Data. This paper was published as a preprint by Xiong and colleagues from the University of Wisconsin-Madison. The abstract highlights the challenges faced by large language models, LLMs, when dealing with long context inputs. Specifically, LLMs struggle with accurately retrieving information and maintaining their reasoning capabilities in such scenarios. To tackle these issues, the authors propose a fine-tuning method that leverages a synthetic dataset designed for numerical key-value retrieval tasks. Experimental results show that this fine-tuning significantly enhances the model's ability to retrieve information and reason in longer contexts. The study also demonstrates the transferability of skills from synthetic tasks to real evaluations, with notable improvements observed in models like GPT 3.5 Turbo and Mistral 7b. Additionally, the fine-tuning on synthetic data does not degrade performance on general benchmarks, unlike other baseline methods that can lead to hallucinations. Recent studies have shown that large language models, LLMs, face significant challenges when dealing with long context inputs and cross-context retrieval tasks. These limitations significantly impact their performance on tasks requiring extensive textual processing and reasoning, such as summarization and question answering over long passages. To address these issues, the authors propose a novel approach involving fine-tuning LLMs on a carefully designed fully numerical synthetic dataset. This dataset is structured for key-value dictionary retrieval tasks, which helps improve the model's performance in both information retrieval and long-context reasoning. Specifically, this approach mitigates the lost-in-the-middle phenomenon and significantly enhances performance on the FLNQA benchmark. Additionally, it results in minimal degradation on other popular benchmarks like MMLU and HelloSwag, indicating that the overall capabilities of the models remain largely unaffected. Another advantage of this dataset is that it contains no factual information, which helps avoid the issue of hallucinations that can arise from fine-tuning on previously unseen knowledge. Figure 1 illustrates a simple dictionary key-value retrieval task. The task involves a list of dictionaries where each key and value is an integer. The goal is to retrieve the value of a specified key, known as the gold key. For instance, the example shows that the value of key 2931 is 8364, and it is located in dictionary 32. This task is designed to improve the retrieval capabilities of large language models, LLMs, in longer context settings. The synthetic dataset introduced in this section is designed for fine-tuning models on two retrieval tasks. The first task is simple dictionary key-value retrieval, where the model is provided with a list of dictionaries containing integer keys and values, and is tasked with retrieving the value of a specified key. An example of this task is illustrated in Figure 1. The second task is a more complex version, multi-subkey dictionary key-value retrieval, where each key is a tuple of subkeys. This task is designed to be more challenging by allowing other keys to share some but not all subkeys of the gold key, and by randomizing the order of subkeys in the prompt. An example of this task is shown in Figure 2. Additionally, to ensure the model focuses on retrieving the correct value without being influenced by the answer format, an answer template is provided. This template helps the model learn the correct retrieval skill rather than the format of the answer. An example of a prompt with an answer template is shown in Figure 3, and the impact of this template on token level loss is visualized in Figure 4, where red indicates high loss and green indicates low loss. Figure 3 illustrates the prompt for a simple dictionary key-value retrieval task, which includes an answer template. This task involves finding the value associated with a specific key in a given dictionary and reporting it using the provided template format. The example shown in the figure demonstrates how the task is structured and how the answer should be formatted, ensuring clarity and consistency in the model's responses. Figure 4 illustrates the token level loss on the target answer when an answer template is provided, right, and when it is not, left. The color coding indicates the level of loss, with red representing high loss and green representing low loss. The presence of an answer template significantly reduces the loss on the formatting part, allowing the model to concentrate on the essential content and develop the correct retrieval skills. In this study, the authors fine-tuned two large language models, Mistral 7B and GPT 3.5 Turbo, on synthetic retrieval tasks. For Mistral 7B, a dataset of 350 samples was used, while GPT 3.5 Turbo was fine-tuned on 150 samples. These tasks involve simple dictionary key-value retrieval. The models were then evaluated on multi-document question answering, MDQA, and flexible length question answering, FLNQA, tasks. The MDQA evaluation involved 20 documents, while FLNQA tasks ranged from 250 to 3,000 tokens. Both chain of thought and non-chain of thought prompting were tested. The findings indicate that fine-tuning on synthetic tasks significantly enhances retrieval and reasoning capabilities without compromising the model's general capabilities. Figure 5 illustrates the performance of GPT 3.5 Turbo and Mistral 7B, along with their fine-tuned versions, on the multi-document question answering, MDQA, task. For GPT 3.5 Turbo, the original model exhibits a U-shaped performance curve, indicating better performance when the gold document is at the beginning or end of the context. Fine-tuning flattens this curve, improving retrieval accuracy across all positions. Mistral 7B initially shows a primacy bias, performing better when the gold document is at the start. Fine-tuning reduces this bias, enhancing retrieval accuracy for documents at the end of the context. Figure 6 illustrates the performance of GPT 3.5 Turbo and Mistral 7B models, along with their fine-tuned versions, on the FLNQA task using chain of thought prompting. The x-axis represents the context size in tokens, while the y-axis indicates the accuracy of the responses. The figure highlights that fine-tuning with answer templates significantly enhances the model's chain of thought reasoning capabilities, particularly for GPT 3.5 Turbo. This improvement is attributed to the model's enhanced retrieval capabilities, which enable more accurate information capture and subsequent answer deduction. Figure 7 illustrates the performance of GPT 3.5 Turbo and Mistral 7B, along with their fine-tuned versions, on the FLNQA task without using chain of thought prompting. The x-axis represents the context size in tokens, and the y-axis represents the accuracy of the model's responses. The results show a significant improvement in accuracy for the fine-tuned models, demonstrating enhanced internal reasoning capabilities even without explicit reasoning steps. Table 1 presents the performance of various models on general ability benchmarks. Notably, Mistral 7B fine-tuned with a template shows a slight improvement in MLU scores. GPT 3.5 Turbo, when fine-tuned without a template, demonstrates an improvement in HLSWAG. The data indicates that fine-tuning on synthetic tasks does not significantly degrade the model's general capabilities across benchmarks like MLU, HLSWAG, GSM-8K, TriviaQA, and NQOpen. Figure 8 illustrates the performance of the fine-tuned Mistral 7B model across three distinct datasets, MDQA, FLNQA with chain of thought prompting, and FLNQA without chain of thought prompting. Each subplot, A, B, and C, provides a detailed view of the model's effectiveness in these specific contexts, highlighting the impact of different prompting strategies on the model's ability to answer questions accurately and efficiently. Table 2 presents the performance of Mistral 7B and its fine-tuned versions across various general ability benchmarks. The table compares the performance in percentage on MLU, HLSWAG, GSM-8K, TriviaQA, and NQOpen. It also includes a comparison with other baselines such as MultiDocQA, IN2, and Needle in a Haystack, showing the changes in performance. The data highlights the impact of fine-tuning on these benchmarks, providing insights into the effectiveness of different datasets. Figure 9 illustrates the performance of the fine-tuned Mistral 7B Instruct v0.2 model on the MDQA benchmark using 120 documents. The figure clearly shows an improvement in performance compared to the original model, highlighting the effectiveness of the fine-tuning process in a longer context setting. The dataset used in this study has a limitation where the distractors are relevant but do not contain the answer, retrieved by a retrieval system based on relevance scores. This affects model performance, as shown in Figure 10, where models fine-tuned on this dataset do not improve in this setting. A potential future work is to incorporate the synthetic retrieval dataset into a larger instruction fine-tuning dataset to observe differences in performance between models trained with and without synthetic retrieval data, particularly in long context retrieval and reasoning tasks. In this study, the authors introduce a novel fine-tuning approach using synthetic datasets to enhance the information retrieval and reasoning capabilities of large language models, LLMs, in real downstream tasks. The results show that fine-tuning on the proposed synthetic data significantly improves model performance on tasks such as medical domain question answering, MDQA, and factual language enrichment question answering, FLNQA, addressing the lost-in-the-middle issue observed in previous research. However, the performance on general benchmarks remains largely unchanged, indicating that the overall capabilities of the models are not significantly affected. The synthetic data used in this study does not lead to hallucinations and avoids the problem of containing outdated information. The authors believe this approach demonstrates the potential of using carefully crafted synthetic datasets for fine-tuning LLMs, and they hope their findings will inspire further research in this area. Figure 10 illustrates the performance of the Mistral 7B model and its fine-tuned variants on the MDQA benchmark with relevant distractors. The graph shows that despite fine-tuning, the variants do not exhibit a significant improvement in accuracy compared to the original model. This suggests that the fine-tuning process, as applied in this study, does not effectively enhance the model's ability to handle relevant distractors in the MDQA task. Thank you for watching.